page 129, section 3.1. Page 129, section 3.1. All right, on the top of page 129, it says, in this chapter, we begin our study of differential calculus, which is concerned with how one quantity changes in relation to another quantity. The central concept of differential calculus is the derivative, which is an outgrowth of the velocities and slopes of tangents that we just studied in chapter 2. After learning how to calculate derivatives, then we're going to use them to solve problems that involve rates of change and approximations of functions. So to begin with today, we start off with them telling us, hey, you know that thing that you've been doing, that limit of f of a plus h minus f of a divided by h as h approaches 0. We called that the slope of the tangent line. We called it instantaneous velocity. We called it instantaneous rate of change. Yeah, that's a derivative. And so that is the basis for our differential calculus that we're looking at beginning in chapter 3. Probably the most common notation that we'll use for derivative you'll see right here, although we are going to have quite a few ways that we denote derivative. But the most common is what you see right here, and that's where we've got the regular f of x, and then we just kind of put a prime mark in between f and x. That represents derivative. So there on page 129, they give us the definition of the derivative, and you'll see it's that same thing that we've been utilizing. So example number 1, it says, find the derivative of the function f of x is equal to x squared minus 8x plus 9 at the number a. So we've done this exact same thing repeatedly, so I just went ahead and filled it in for you in your notes so that you could just follow along and not have to write it all out again. But if they ask me to find the derivative, that's just that same definition we've been using, so I'm going to use that same thing. And they told me to find the derivative at a, so that just means we're going to leave a in and create basically a formula for the derivative. If they had asked me to find the derivative at a particular number, like find the derivative at 5, then I'd be putting 5 in for a, just like we did for slope of tangent and instantaneous velocity. So since they told me to leave a in, I'm going to go through and I'm going to start with put a plus h in the place of x in that formula. So that would be a plus h squared minus 8 times a plus h plus 9. A plus h squared minus 8 times a plus h plus 9. Then I'm supposed to subtract f of a from that. So that just means put a in the place of x. So that'd be a squared minus 8a plus 9. So a squared minus 8a plus 9, subtract that whole thing. And then divide it by h, divide it by h. All right, so now we're going to simplify. A plus h squared, we're just going to FOIL out. So a plus h times a plus h gives us a squared plus 2ah plus h squared. Distribute the negative 8 to the a and the h, so negative 8a and negative 8h. And then we've got our plus 9. Then we're going to subtract this whole function, so every single sign will change. So it'll be negative a squared positive 8a minus 9. So negative a squared positive 8a minus 9, all still over h. And as we've seen in the past, then everything starts dropping out, right? Our a squared and our negative a squared cancel. Our negative 8a and our positive 8a cancel. And our positive 9 and negative 9 drop out, so that what we're left with in the numerator, every single one of those terms has an h. So I could take out that common factor of h to cancel top and bottom, and then what I'm left with will be well behaved, that I can use direct substitution. So I'll go through and I'll put 0 in the place of h. So that would give me 2a plus 0 minus 8. And notice again, we've copied our limit notation all the way through until we actually put 0 in for h, and then we don't use our limit notation any longer. And so that gives us 2a minus h. So the derivative of x squared minus 8x plus 9 would be 2a minus h, or I could use any variable there. It could be 2x minus h, or 2y minus 8, or whatever they happen to want me to use. So 2a minus 8 is our derivative. So then for example 2, it says find an equation of the tangent line to the parabola, and it's that same equation, right? Y equals x squared minus 8x plus 9, and find that at the point 3, negative 6. Well, if I understand that derivative and slope of the tangent are the same thing, then I can say, hey, I just found the derivative to be 2a minus 8. That would be the same thing as the slope of my tangent line. So instead of redoing this, I could just say, okay, if I want the slope at 3, let's put 3 in the place of a, and I figure out my slope is -2. And so now I have a point and I have a slope, and I can do point slope form, or I can do slope intercept form, or I can do standard form, whatever they ask me for. So they're trying to help you make those connections there, that slope of the tangent line and derivative are the same thing. All right, look at example number 3. For example number 3, it says, let f of x be equal to 2 to the x. Estimate the value of the derivative in 2 different ways. First, by using definition number 2. Okay, so definition number 2 is that same one that we were just using, right? F of a plus h minus f of a divided by h, limit as h approaches 0 of that function. So when they ask me to find the derivative at 0 using that definition, I'm going to go through and I'm going to put 0 in the place of x. So where we normally have f of x plus h, I've got f of 0 plus h. And where we normally have f of x, I have f of 0. All right, so if I plug those in, if I plug in 0 plus h, that's just h, right? So f of h then minus f of 0 divided by h, right? So f of h tells me put h in the place of that x right there, so that would be 2 to the h. F of 0 tells me put 0 in the place of that x right there, so that'd be 2 to the 0, so 2 to the 0 would be 1, divided by h. And I'm stuck. Because up to this point, anytime I was asked to find the limit, it was something that I was able to calculate, right? Like maybe I had to factor and cancel, or maybe I had to rationalize the numerator, or maybe I had to combine fractions with a common denominator, or multiply top and bottom by the least common denominator to get rid of a complex, something. But I was able to simplify it down, and it was well behaved, and I could use direct substitution. That's not the case here. If I use direct substitution, it's not well behaved. I get 0 in the denominator, and I can't think of anything algebraically I could do to simplify that. So I'm going to go back to the very first way that we learned how to evaluate limits, and that was make a table of values. Because if I don't have a way to algebraically find the exact value, I'm going to have to go back to coming up with an educated guess by looking at a table. And so that's what they asked me to do in example A, or in example 3 part A, is to create a table of values, make successively smaller values of h to get an approximation of what this might be. All right, so if I go through and I take what we just had, 2 to the h minus 1 over h, and I put that into my calculator, and I go through and I make a table looking at as I'm approaching 0 from the left and the right, using those same type values that we normally do, then you can see the y values that that creates in my table. And so looking at that, it does look like the limit from the left and the limit from the right are converging on the same value. It looks like they're converging on a value of 0.693. So that would be my approximation. That would be my guess. It's just a guess, but I think my derivative would be 0.693 at 0. The second part of that says, since we know that the derivative is the same thing as the slope of the tangent line, why don't I use slope of tangent line to help me? So remember that we could take this curve that we have right here, and we could draw a tangent line right there at 0, and if we found the slope of that tangent line at 0, then that would tell me what the derivative at 0 is. And so what they suggest to me in part B is interpret the derivative at 0 as the slope of the tangent, and use a graphing calculator to zoom in on the graph of y equals 2 to the x. So here's what they suggest. I started with, you don't need to do this, you can just watch. I started with a zoom decimal, and I zoomed in. You can see like my scale is almost completely gone down here now, and I zoomed in, and I zoomed in again until this almost made a straight line. Here's their thought. If I zoom in enough on that curve, it's going to become almost linear, right? And so then if I were to hand draw a tangent line at that same point, I would be getting the same slope. And so if I've zoomed in enough on my curve where it's almost linear, I'm going to come a tiny bit to the right of 0, just using my trace button. I came a tiny bit to the right to see where I was, so I got an ordered pair. And I came a tiny bit to the left of 0, and I got another ordered pair. So if I went through and I found the slope using those two ordered pairs, because I've zoomed in so much on my graph that it looks pretty much linear, it'd be the same thing as if I hand drew a tangent line and I was zooming in on it and pulling 2 points off of it. So I could go through and do y2 minus y1 over x2 minus x1, and I get an approximation for my derivative of 0.692. Now, that looks pretty good, because I got 0.693 up here, I got 0.692 down here. Kind of looks like I'm on the right track. The purpose of the second part of this example is, again, to reinforce to us slope of the tangent line and derivative are the same thing. However, if I was going to do the second part right here, the B part here, I would have to have a graphing calculator to do that, right? There's no way to do that without the graphing calculator. If I have my graphing calculator and I'm looking for the slope of the tangent line or the derivative at a point, my calculator will find that for me. So I'm not going to use this method that's going to give me just kind of a guesstimate if there's a way that my calculator can give me a much more accurate answer, right? So let me show you, there are actually multiple ways that you can get your calculator to find the derivative. So let me show you a couple of those ways. Now, let me preface this with your calculator can do a numeric derivative. It cannot do a symbolic derivative. Let me show you what I mean by that. Let's say that we had a basic equation, f of x is equal to x squared plus 5x, okay? I know that the derivative of that is 2x plus 5. If you actually went through and you did your formula, f of a plus h minus f of a divided by h, and you took the limit of that, then we would end up with a derivative of 2x plus 5. My calculator can't tell me that. I can't say f of x is x squared plus 5x. Please tell me the symbolic derivative. That's a symbolic derivative. It gives me the derivative in symbols. It can graph that for me. I can tell it to graph the derivative, and it'll graph that linear equation right there. And then from there, I might be able to pull off the equation, particularly if it's linear, I could. What my calculator can do, however, is a numeric derivative. Like I could give it f of x and say f of x is x squared plus 5x. Please tell me the derivative at 5. And it can do that. It can go through and tell me that that derivative is 15. And it will be accurate. And that's how it actually graphs the derivative as well. It just goes through and plots a whole bunch of points and then graphs it. So I can get my calculator to tell me the derivative at 0. I can't get it to tell me the derivative overall, but I can get it to tell me the derivative at 0. So here's how I could do that. I'm going to go to y equals, and I'm going to put in my equation. Remember, the original equation was 2 to the x. So it wasn't that 2 to the x minus 1 divided by h thing, or x. That was what we were using for limit. I need to go back to the original equation, 2 to the x. Then I'm going to go to second trace, which is my calculate menu, which is where all the best buttons on my calculator are anyway, right? So I'm going to go to second trace, which is calculate. Number 6 down here is derivative. That's going to be one of the other symbols that we use for derivative that we'll learn a little later on. But basically dy dx is basically like saying the derivative of y in terms of x, or the change in y over the change in x, or the instantaneous rate of change of y with respect to x, or however you want to think of that. So I'm going to choose number 6, and when I do, on my graph, I can start typing any number that I want to. It will automatically put itself somewhere. As soon as I start typing, it'll take whatever number I give it. So like if I wanted to find the derivative at negative 1.234567, I would just start typing and it would take that, okay? I want to find the derivative at 0. So if it doesn't automatically pop up at 0, you just tell it 0, enter. And when I do, it tells me your derivative is 0.693144724. I can do that much quicker than I could do any of this up here. And you can see this wasn't even leading me to the correct answer to 3 decimal places, where this is giving me the correct decimal, or the correct answer to 8 decimal places, right? So that's one way I can do this. There are several ways that I can do this. That's one way. Here's another way, and I actually like this one better. So I'm going to go back to y equals, and I'm going to put my equation in y equals 2 to the x and graph it. So y equals 2 to the x, and hit graph so that you've got this picture on your screen. All right. Then I'm going to go to second program. That's my draw menu. Second program is my draw menu. I actually showed you how to do this last year, but that's been a little while. And on my draw menu, I'm going to go down to number 5. And I can tell it to draw a tangent line anywhere I want it. And so again, it will automatically position itself somewhere, but I can just start typing. Again, whatever number I type, it'll take. Negative 1.23456. It'll take whatever I type. So I'm going to tell it 0, enter. And when I do, there's my graph, there's my tangent line, and here's the equation for my tangent line. Now, when we see that equation, that's a line. It's y equals mx plus b, right? What of that is my derivative? The slope, right. So I can look at that and say y equals mx plus b. There's my slope right there, and that's the exact same thing that we got up here. The reason that I like this better is it's the same number of key presses, right? It takes me the same amount of time. But half of the time when they ask me to find the slope of the tangent line, that's part A, and part B is to find the equation of the tangent line, right? So I might as well get 2 for 1 here while I'm at it, plus I get a pretty little graph to go along with it too, okay? So those are just a couple of ways that I can do a numeric derivative on my calculator. Examples 4 through 6 give us what I call a preview of coming attractions. Over on page 132 on the top of the page, they reiterate what we've already said, that derivative is the same thing as instantaneous rate of change with respect to x when x equals a. But there's something that they kind of slide in. Below that definition on the top of 132, you've got 2 paragraphs. Look at the second paragraph that starts with in particular. It says, in particular, if s equals f of t is the position function of a particle that moves along a straight line, then the derivative of f of a is the rate of change of the displacement s with respect to the time t. In other words, the derivative at a is the velocity of the particle at time t is equal to a. So basically I'm talking about it's the velocity at the instant when t is equal to a. That's instantaneous velocity. But from here on out, anytime they ask me to find velocity, I'll automatically know that they want me to take the derivative. The last sentence in that paragraph right above example number 4 ought to be like in bold print as a definition or something. I'm not crazy about the fact that it's just kind of slid in there. It says the speed of the particle is the absolute value of the velocity. Now we're going to see that several times again, and they will stress it a little bit more when we see it again, but I would go ahead and point that out to you there, that you can have a positive or a negative velocity representing something speeding up or slowing down, but you can't go in negative 10 miles per hour. Speed is never negative. So you would always take the absolute value of your velocity to get your speed. So again, that really should be emphasized more than it is there. So in example number 4, they go through and they give you a particle motion problem where they're talking about the position of the particle, and they ask you to find its velocity after 2 seconds, and you'll notice they just do the derivative at 2 because the velocity at a particular instant is the same thing as the derivative. And then at the end of that problem, they say, if you wanted to find the speed, you would just do the absolute value of that. Example number 5. AP loves for us to interpret our results. Okay, you just got this answer. What does that mean? What does that represent? What did you just find? So let's look at example number 5. Example 5 says, a manufacturer produces bolts of a fabric with a fixed width. The cost of producing X yards of this fabric can be represented with the equation capital C is equal to F of X dollars. So if we were to take the derivative of f of x, if we were to take the derivative of that cost, what would that mean? What would we be finding? So again, they're really jumping ahead of themselves here. This is something we're going to talk about the interpretation of in this whole chapter, but just a really good introduction for us here. if derivative is rate of change of one quantity with respect to another, if we're talking about the rate of change of the cost, if I make 100 TV sets, they might cost me $1,000 each to make, because I have to pay for the building and the factory and the equipment and the employees and the benefits and everything else. If I make 1,000 TVs, they might only cost me $75 each to make. If I make 1,000,000 of them, they might cost me $20 each to make. There is a rate of change of the cost that depends on the number of units I'm making. And that is exactly what derivative talks about in this situation. The derivative would be the rate of change of the cost with respect to X, the number of items that you're producing. And so when we talk about the label for that, what would the units be? It would just be if it's the change in cost over the change in units, it would just be whatever I was giving my price in, dollars or pennies or thousands or whatever, over whatever my denominator might be, in this case, however many units that I'm making. So if those units, were again in single values or thousands or whatever. Then for B, it says in practical terms, what does it mean to say that the derivative of 1,000 is equal to 9? Well, basically what that's saying is that after I make 1,000 yards of fabric, the rate at which the production cost is increasing is $9 a yard. So it's increasing 9 times as fast. And we also could say the cost of manufacturing the 1,001st is about $9. So if I wanted to look at just that individual one, that's kind of like the rate of change of the one at that production level. And then for C, it says, which do you think is greater, the derivative at 50, at 500, or at 5,000? And we get this idea that the more you make, the cheaper it is. Obviously, it's going to be cheaper to make 5,000 of them than it is going to be to make 500 or 50. And sometimes that genuinely is the case. But at some point, you are going to hit a place where you have to go open another factory, or you have to pay overtime, or you have to buy another machine to manage that production level, or your supply and demand don't match up anymore and you saturated your market and then you're not able to sell them for as much. So that's not always going to be the case, and we will work on something called a marginal analysis later on that kind of analyzes all of those factors. So again, examples 4 through 6, preview of coming attractions, but really good preview in example number 5 of the types of things that AP will eventually want us to be able to interpret from this information. Okay, so here is our homework for tonight on page 134. Page 134, we're doing 9, 11, 15, 25. Challenge 27, which 27 is like example number 5 that we were just talking about. So page 134, 9, 11, 15, 25. Challenge 27. And 27 is like example number 5 that we were just talking about.